I'd like to welcome everyone today to the sixth and last session of Physics 101. And today I'm going to set all of your heads spinning because we're going to talk about the physics of rotation. So some preliminaries. We have talked about pieces of this before, but I wanted to give you a unified overall summary of conservation laws. There are three conservation laws that we have strong theoretical reasons to believe are a fundamental property of nature. And that is the conservation of the total amount of energy in any closed system or in the universe, the total amount of linear momentum in each of the dimensions of space, again, in a closed system or in the universe. And as we'll discuss today, the total amount of angular momentum, the rotational momentum that we're going to talk about. And all of these things stem from our understanding of general relativity primarily. And we have strong reason to believe that they are fundamental properties of the universe. Now, there are three other conservation laws that we have excellent experimental validation of, but we don't have a strong theoretical motivation to explain why we expected these things to be conserved. So it's a different kettle of fish here. So we know to extremely high precision that the total amount of electric charge in any interaction that's been observed is conserved. So you cannot create an isolated positive charge without creating an isolated negative charge of exactly the same magnitude. And you can't destroy a positive charge without destroying an equal negative charge. Also, the total number of quarks is conserved and the total number of leptons is conserved. Now, these were not known in classical physics. These were discovered in the 20th century, but nonetheless, I put them on the list just to make the list complete. So quarks are the particles that participate in the strong nuclear force. And all of the nuclear particles, the particles of the nucleus of all the atoms are made of combinations of quarks. And they come in 6 different types, but 2 of them are stable long-term and 4 are not. So there are really 2 quark types that are important, particularly if you're talking about atoms and molecules. And the total number of each of these types of quarks is conserved. So you cannot create an extra quark of one type without destroying a quark of the same type. The weak force violates the conservation of individual types of quarks, but not the violation of the total number of quarks. And similarly, there are 6 different types of leptons, of which only the neutrinos, we believe, have an infinite life. The electrons have an infinite life because none of them have anything else they can decay to. And there are 2 other leptons that have a very short life. But all of that aside, the total number of leptons is conserved in any interaction that's been observed. But again, we don't have a fundamental theoretical basis for claiming that these last 3 conservation laws are an intrinsic fundamental part of nature. It's just that we observe that they seem to be. Any questions about those? Okay, so let's talk about the motion of 3-dimensional bodies. We have in the past talked about motions of bodies, and we weren't very specific, but really what we were analyzing, for instance, in the trajectory of a cannonball that we talked about, what we were analyzing was the motion of a object of 0 dimension, of 0 size. So Newton's laws really fundamentally pertain to a point particle. And we sort of ignored that issue because obviously a cannonball or any other macroscopic object is not a point particle. Now, it turns out there's this wonderful theorem that Newton proved, and which I provide in one of my various books, and I forgot which one at the moment. There is a theorem that you can prove that shows if you have a three-dimensional ball and the ball has uniform density, that the gravitational force that ball exerts, or the gravitational force that it feels that's exerted upon it by something else, is independent of the radius of the ball. So you can take a cannonball that's 10 centimeters in diameter, and you can treat it as if its radius is 0, as if it's a point particle. And then you can apply all of Newton's laws. It's not immediately obvious to me, at least, why that theorem should be true, but if you go through the math, all of it works out. If you sum all the interactions of all the different particles in a solid ball, as long as the ball is symmetric, all of the different contributions will cancel out in a way that you can just take the sum of all the masses as if they were located in the same place. So the density can vary with the radius, but it can't vary with the angles. Okay, so the principal equations from Newtonian physics that apply when you have an object, a single body moving in 3 dimensions. All of these italicized bold quantities are vectors. So the vector force, the vector acceleration of Earth is straight downward. This is the velocity, and this is the mass times the acceleration. Okay, now let's talk about a body that's composed of n particles. N would be an enormously large number, like trillions of trillions. And we will allow the body to have each of the particles to have a different mass. So the mass of the nth particle is this quantity here. And each of the particles has its own position. So there's a vector that shows us where that nth particle is. And we have these values for every one of the n particles, capital N particles. So then the total force is the sum of all the individual. This is the force of the nth particle. This is F equals ma for the nth particle. The force acting on the nth particle, which has a certain mass, results in a certain acceleration. And if we just add these all up, this is the symbol for adding all of the n's up, then we get this equation. And it turns out that the derivative and the arithmetic sums are, what is the proper word? Distributive. So this relationship applies. You can take the derivative of the sum, or you can take the sum of the derivatives. And so we move the sum on the inside, and now we have this other equation, which I'm going to take to the next page. And we can write it, we can write that equation this way. M is the sum of all the masses, and R is the weighted sum of all the positions. So weighted sum means if something weighs twice as much as something else, then you include it with a factor of 2 in the summation. So now we can talk about this body as a whole and not worry about all of the inner workings of the body. We don't have to worry about all the forces between all the particles. We can just treat the cannonball as one contiguous object. And R is called the position of the center of mass. So the center of mass is defined by this equation. It's what you would think. If you were to hold it by the center of mass, it wouldn't spin, it would turn, because gravity is acting on it on the left side is equally with the right side, and the front and the back and so forth. The center of mass is the point that is stationary if there's no external forces. And the motion of the center of mass is actually what Newton's laws really describe. Okay, now let's look at this in a bit more detail. Let's imagine that you have a force A coming from the outside. This is an external force, and this force is acting on each of the particles in the body. And B are the forces that the particles exert on one another. So B are the internal forces that hold the ball together, and A is what the cannon does to the cannonball, shoots it out, exerts a force on the whole ball. So we can take the sum of all of the forces, and the sum of F will be the sum of A plus the sum of B. And by Newton's third law, the sum of all the B's has to be 0, because for every force from particle A acting on, from particle X acting on particle Y, there has to be an equal and opposite force from particle Y acting on particle X. So all of the internal forces have to cancel out, and we can ignore them, which is great because otherwise life would be way too complicated. And therefore, the total force on the body is simply the sum of all of the external forces on each of its particles. So far, the fact that we've got a three-dimensional object instead of a point hasn't really made life any more complicated. So this is a restatement of what we had before. So the total force on the whole body is the sum of all of the external forces acting on the particles of the body. And therefore, if you have an isolated system with no external forces, then the total force is 0. And that means there's no change in the total momentum. The rate of change of the total momentum is 0, which is Newton's third law. Because of Newton's third law, the total amount of momentum has to be constant, and this is a detailed explanation of why that applies to large objects as well as points. So, what does all this mean in more practical terms? Imagine that you have a spaceship far away in outer space where it's in a completely weightless condition, unaffected by the gravity of the Earth or the sun or the stars or anything else. Then the center of mass of that object can't move because there's no external forces and all of the internal forces will cancel. So if you imagine that you start off with the crew sitting at the bottom, if the crew moves to the front of the ship, then the ship has to move backwards. The ship has to move backwards because the total center of mass has to stay in a constant place. So if the crew elects to move in one direction, the ship has to move in the other. Now the ship weighs a lot more than the crew, so the ship isn't going to move as far, but the total center of mass has to remain constant. And that can also help us understand how a rocket works. If you have a rocket in isolated space and it has a full fuel tank, and so the total mass of everything, including the rocket housing, the payload, and the fuel is this m0, the original m at times 0. And let's assume that we define the spaceship to be stationary at time 0, to have 0 velocity. And at that instant in time, the rocket engine fires. And it starts ejecting fuel at a constant rate. A constant amount of mass of fuel is ejected in each increment of time. This is the change in the mass for a change in time, and we're going to shoot the fuel out the back of the rocket at velocity u. U is a constant relative to the rocket, and v is the velocity of the rocket, and that's going to change over time. The rocket's going to go faster and faster, and its mass is going to become less and less because it's ejecting fuel out the back, and the fuel has mass. And in fact, it's the mass of the fuel being shot out the back that pushes the rocket to the front. So by conservation of momentum, the rate of change of total momentum has to be 0 because there's no external forces. And so the change in the momentum of the ship has to equal the change in momentum of the fuel. So the change in the momentum of the ship is the change in its velocity times its mass at any given time. The mass is changing, the velocity is changing. U is a constant that's with respect to the rocket. And this is the change in the mass of the ship. So you run through the math and you come up with this equation, which looks a little weird, but this is the mass of the rocket at any point in time divided by its original mass. The mass is going down, so this left-hand side is less than 1, and that's good because the exponential of a negative quantity is less than 1. This is the velocity that's achieved at a certain time, and this is the velocity of the fuel coming out. And if you take a typical situation for a typical rocket that we would actually launch, you find out that if 90% of the original mass is fuel, then by the time you burn all that fuel, the rocket will be moving at about 2.3 times the velocity that the fuel was ejected at. And this is actually the number that people like NASA use for rocket maneuvers. You need 90% of the rocket to be fuel in order to get the rocket up to just over 2 times the exit velocity of the fuel. And if 90% of the rocket's original mass is fuel, and a typical number is that 9% of the original mass is the structure of the body of the rocket itself, then you come to the unfortunate conclusion that only 1% of the original rocket mass can be payload. You know, the astronauts or whatever you're delivering to outer space. So 99% of the mass of the rocket is stuff that is not going to get, that isn't going to serve a useful purpose on arrival. So the rocket business is very expensive because these ratios are so unfavorable. Any questions about these equations or the rocket? There was a question that was asked previously about how rockets work. And I hope that this was a sufficient answer.
Yes, but Bob, can I go back about 4 slides? I just want to check some math there. Make sure I understand what you're doing.
I'm trying.
Sorry.
No, it's you tell me when.
Okay.
More? Back more?
More. Back more. Back more. All right. So let's see. So, okay. Okay. So take me from F equals the second derivative of that sum.
Yes.
Then go to next slide. This is more math than physics. Okay. So now you.
Yeah, but the math is the physics. I'm sorry. It would be better if there were no. It would be easier if there were no math and physics, but we would learn nothing.
Okay.
Okay, and that's my plug.
Okay. That's good
Let me,
motivation.
let me not interrupt your question any further. Okay, go on.
Okay, so you've taken you've taken the sum of the individual masses.
Are we at the top here?
Well, we started at the top, and
Yeah.
then you've moved. We can write this, and you've taken the sum of the individual masses out of the second derivative.
Right, because we're assuming that the particles' masses don't change. Yeah, there's a critical assumption here. In classical physics, the mass of these particles is never going to change.
And you can take a constant out of a derivative, out of the second derivative.
Right, because it's not changing with respect to time.
Okay.
So this is the rate of change of the rate of change. But if it never changes, then it's just a number like 7.
All right.
And you can move 7 out of the time derivative because 7 is a constant.
Okay. So now I'm happy here.
Yeah.
And then you define M as the sum of the individual masses.
Right.
And then you define R. You put the masses back in.
Yeah. So you could look at if all of the particles had the same mass, then you wouldn't need the subscripting. You could just take the M out, and the sum of M over M would be 1, and you'd be looking at R being just the average of all the positions.
Which you'd think sort of at the gut level.
Yeah, at the gut level, that's what you'd expect. The center of mass is the average of where everything is, right?
Right.
And if the particles all have the same mass, that's what this equation says. But if some of the particles weigh more than others, then they count more.
Okay. Peace. Thank you.
Okay.
I'm happy now.
Are you happy with the rest of these slides also?
Yes, thank you.
Are we going back to the rocket ship?
Right. I'm with you through the rocket ship. Thank you.
Right. Any other questions? It's good that you ask these things because that's why it pays to have a live conversation, right?
Right. Rather than going over the view graphs at 10 o'clock at night and saying, what?
Yeah, or reading a book, right? So you ought to read the book and you ought to listen to the live conversation because each of them offers something that the others don't. Okay.
Yeah.
So now we talked about the center of mass. We talked about how the center of mass moves. And now let's talk about rotations. So rotations in 3 dimensions are a little bit complicated. And we do our best to simplify as much as possible. And so the mathematician Euler, centuries ago, came up with a way to view 3-dimensional rotations in a simpler fashion. And that is that any 3-dimensional rotation can be decomposed into 3 separate rotations, each of which occurs in 2 dimensions. And it's a lot easier for us to think about a 2-dimensional rotation. So the way this works is you start off with this oval here, as you can imagine, that's a flat disk. And this z-axis, small z, is the axis of symmetries. So this line is perpendicular to the disk, and we rotate about this axis z some angle alpha. So first thing we do, the first rotation is we take the object and we rotate it about the vertical axis by some angle alpha. So that gets us to the point where we now have this direction that used to be X has moved over to this direction that we now call N. Okay, now we take this disk and we tilt it by angle gamma. So we end up with this oblong disk. And now we do a final rotation by axis capital Z by, I'm sorry, beta was the angle of tilt and gamma is the final rotation. So alpha, beta, gamma. Okay, and there are complicated equations that I'm not going to inflict on you. That all sorts of combinations of sines and cosines of all the different angles taken in more ways than you would care to guess. It is important, however, that you keep track of whether these rotations are in some sense positive or negative. And so we need a convention so that we all talk about rotations in the same way. And that convention is called the right-hand rule. So you lefties are out of luck here. This is the right-hand rule, and it's universally applied. So there's no democracy here. The right-handers rule. So if you stick your arm out, and that's the position, you're pointing at the position of an object or a body, and then the body turns so that you're curling your fingers, then the axis of rotation is the direction of your thumb. If I did it with my left hand, the thumb would be pointed down. This is the same direction of rotation, but the thumb is pointed down. So that's wrong. This is the right way to define a rotation. And we define rotations in terms, angles in terms of radians, because mathematically that's simpler. There are 2 pi radians in a full circle. So in 90 degrees, which is a quarter of a full circle, there are pi over 2 radians. And one of the nice things about radians is the length of this arc in yellow is r times the angle. So if you had a larger r, then the arc would be bigger. And if you had a larger theta, the arc would be bigger again. And the product of the two is the length of the arc. And that is easy to confirm because this is a quarter of a circle. And so if you multiply this by 4, you get 2 pi r, which is indeed the circumference of a circle. So all of this makes sense if you measure angles in radians and if you keep the right-hand rule. I remember distinctly a Caltech final exam in which I saw someone 2 rows down doing like this throughout the whole exam. And there was a moment in which there was a scream of terror and he started erasing stuff for the last 4 pages. That's not where the problem you need to have. Okay, so let's talk about rotations of bodies composed of individual particles. And we're going to do the simplest type of rotation. We're going to consider the body to be rigid so that all the particles have to move in unison. All the particles maintain the same distances between them that they had before and the same orientation. And we're going to rotate about just one axis. Axis of rotation will be called Z. And so we're going to look at what happens in the plane perpendicular to Z, which is the plane in which we can make a 2-dimensional graph in coordinates X and Y. So imagine that you had this rectangular object and we're going to look at the point P on its corner, and we're going to rotate by some small angle delta phi. So P was here to begin with. When we rotate, it moves to Q. U is the vector that takes P all the way to Q. And so Q vector equals P vector plus the U vector. And you run through the math, and this is what you get. So if you work on this triangle here, you can figure out that these are the new values. These are the coordinates of the vector that takes you from P to Q. And if you write it this way, then the change in X is minus Y times the angular rotation angle, and the change in Y is plus X times the rotation angle. So this is the most convenient way to consider it. And if you're rotating at a constant rate, so this thing is turning at a constant angular velocity, the angular velocity is called omega, then the rate of change of X, we can just the rate of change in phi. So the velocity in the X direction is minus Y times the angular velocity. The velocity in the Y direction is plus X times the angular velocity. So you have this sort of broken symmetry here. The velocity in X is proportional to Y, but with a minus sign. The velocity in Y is proportional to X with a plus sign. And you have to have the opposite signs, otherwise the thing is not going in a circle. Otherwise, these quantities would get larger and larger and larger, which means it gets further and further away from the center. In a rotation, it doesn't get any further away from the center. It always stays at the same distance. And so that's why you need the minus sign to keep these quantities matching. X squared plus Y squared will always be R squared, according to Pythagoras. Okay, so if you take the squares of the velocities, then this is the total velocity in the XY plane. This is R squared, as we just described, according to Pythagoras. And so the linear velocity is R times the angular velocity. Angular velocity is how rapidly the angle is changing, and the linear velocity is how rapidly the position is changing. And of course, if your radius is twice as far away, then the linear velocity is going to be twice as much for the same angular term, right? Okay, so we completely mastered Newtonian physics in the linear version, in which things were moving in more or less straight lines. And now we are looking at the angular rotational motion, and we have similar equations with some differences. So we used to define the position in terms of R, and the position now is primarily in terms of the angle. The velocity is the rate of change of position, and the angular velocity is the rate of change of the angle, and acceleration is the second derivative. We used to just talk about mass, and now we have to talk about something a little more complicated, which is called the moment of inertia, I, and we will talk about what that is in the next few slides. We had a linear version of force, F equals ma, and now we have an angular version, which is tau equals R cross F. And tau is also a vector, so this should be italicized and bolded, and I neglected to do that, but this is a vector, and this is a peculiar vector. So if you have a radial distance from the center of rotation to the point of the object that you're talking about, and you exert a force on the object this way, then this torque is not what you would think. You might think the torque is pointing in the direction of the force, but this is the cross product. So the torque is are perpendicular to the radius, and it's also perpendicular to the force. So the torque is pointed this way. The force is this way, the torque is this way. So when you push on something that's turning, you're going to create a torque which is in a perpendicular direction.
So Bob, we
Yeah.
can't see your hands because they're hidden behind Robert Passione.
Can you see my hands now?
No, come up. They almost
Oh,
have to be.
I see.
Yeah, yeah,
It's line
yeah,
of
right.
sight. Okay, I was
Right.
changing something. Okay, can you see my hands now?
Yes. Well, a little. What makes it difficult is, yeah, that now we can see them. The video has Robert Passione down in the lower left, which masks your hand generally. So your hands have to be high, almost to your face level.
Tell me when you see my hand.
Now. Oops,
Now?
No. Now.
Now, okay.
So if it's at about your face level, we can get it.
Okay, so you see my hand?
Yes.
Okay, so this is the radial distance. This is the R vector. That my elbow is the place where rotation is going to be the axis of rotation. So you measure from that to the position of the object you're talking about. So this is R. And now if the force applied to the particle is in this direction, if F, then the torque is perpendicular to both R and F. So the torque will be pointing up, not as my index finger, but as my thumb. Can you see all that?
So the torque becomes vertical relative to your arm.
Right.
Okay, thank you.
Did everybody else get to see that? Andrew,
Yeah.
I'm really glad you said that because I don't see what you see. So if you don't see it, then I certainly.
Robert, it really has
know
to be
about
right in front of your face for us to see it.
I'm sorry?
It really needs to be right in front of your face for us to see it. Yeah, exactly.
All right.
Sorry.
All right. I'll hide behind my face. I mean, behind my hands. Okay, so the torque has this weird property we just discussed. And there's in the linear business, there's the linear momentum is mass times the linear velocity. And here you have another one of these cross products. The angular momentum L is the radius and with a cross product of the linear momentum. So the L is pointed in the same direction as the tau when the force is applied in the direction that's of the momentum. So there is an opportunity to be confused here about which direction the torque is going to be pointing, and an opportunity to be confused about which direction the angular momentum is going to be pointing. And we will try to clear that up on the following slides. And lastly, kinetic energy, the energy of motion is 1/2 mv squared in the linear Newtonian case. And in the case of angular motion, there's a kinetic energy of a moving body that's rotating around. It has kinetic energy as well. And you can either calculate it this way, or equivalently, you can calculate it this way. It's 1/2 the moment of inertia times the angular velocity squared. So this looks a little bit like this with the substitution of the letters. Any comments about this slide before I move on? Okay, so let's look at these quantities that are a little weird. Again, the rotation is going to be in the positive direction here. And that means that the axis of rotation is Z, which is pointed toward my face out of the screen. And so we have the vector R from the axis of rotation, which is x equals y equals 0. That's the Z axis. And there may be a force applied to the particle that causes it to turn. Now, we're not allowing the particle to shoot off into space. The particle is somehow constrained to rotate about the center. Maybe this is part of a solid body like a bowling ball. And so the motion of the object will be to go round and round when you apply this force, even though the force is not exactly in the optimum direction. Work is force times the distance against which the force, you move against the force. So the change in position, and it's the dot product. So if you move in the same direction as the force, then this is the work released. If you move in the opposite direction of the force, then this is the work that you have to apply in order to push against the force. So the dot product is this in 2 dimensions, and we know what dx and dy are in terms of the angle changes. And so we can write the work done is the torque times the change in angle, where if we define the torque to be this. And this is exactly the same form as we had on the previous slide. This is the R vector with a cross product of the F vector, the force vector. So in the previous slide, do I get the previous slide? That's this equation, R cross F. So in 2 dimensions, this is R cross F, and tau would then be in the Z direction, pointing out of the screen. It's along the Z axis, the axis of rotation, and it's pointing out of the screen. So when you apply this force, the object doesn't move that way. The torque is perpendicular to the screen. This is a restatement of what we said before. And so if X is entirely if the force F is entirely in the plane, no component along the Z axis, then the torque is entirely along the Z axis. Okay, now let's take this a little bit further. So we can write the force as the rate of change of momentum. So I did that here. And then what is the rate of change of momentum? We're assuming the mass is a constant, so we take it out of the derivative. So this is the rate of change of velocity. So that is, if you want to say the force in the y direction is m times the acceleration in the y direction, that's what this is. And in the y component is the opposite thing with the x acceleration. And we can now move these derivatives outside, moved everything inside the derivative, moved the derivatives outside. That's not immediately obvious, but I will not justify it. You can do the calculation and you find out that there's a couple cross terms that cancel. That's a little bit of algebra that I'll let you guys do. So we have the torque is the rate of change of this stuff in brackets. Okay. Now we move to the next slide. Here's the same equation before. And now I go back to mass times velocity is momentum in the 2 directions. And now we define angular momentum. So torque is the rate of change of the bracket, and the bracket is equal to angular momentum. So torque is the rate of change of angular momentum, torque a vector, angular momentum a vector, and that's a very similar looking equation to the linear case. So we have taken what is a relatively more complicated situation. Rotation is more complicated than linear motion, but by defining torque and angular momentum in this particular way, we are able to keep the same form of the final equation. And so whatever solved this equation is going to solve this equation. Since we learned how to deal with this equation, now we know how to deal with this equation. And this is the equation for a two-dimensional angular momentum, and this is the equation in 3 dimensions. It's again the cross product. And as it says, this is the definition of what angular momentum is. Questions? This is not supposed to be easy. Okay, and now I want to demonstrate that if you have an isolated system, the total amount of angular momentum has to be conserved, just as the total amount of linear momentum is conserved in an isolated system. So we start off with a system that's simple, just made of 2 bodies, A and B. And whatever force exists that operates, that A exerts on B, by the third law of Newton, there's an equal and opposite force that B exerts on A. And these 2 arrows aren't in exactly the same place. I displaced them so that you could see that there's 2 colors going on here, but actually the arrows should align perfectly, and they should have exactly the same length and exactly opposite directions and exactly the same position. They go from the center of A to the center of B, both of them. Okay, so if you with torque, you have to calculate torque with respect to the axis of rotation. When you calculated force, you didn't have to worry about what was the center of our coordinate system, but when you calculate torque, you do. So, and when you calculate angular momentum, you do, because they're only defined relative to the axis of rotation. So the torque that you would calculate depends on which point you're going to rotate about. But you can pick any point P, and because these vectors are equal and opposite, and they go from the same start to the same finish, then they're going to completely cancel. So there isn't going to be a torque exerted by the internal forces. And it doesn't matter which point you reference, there is no torque that's going to cause the body to rotate because of any of the internal forces of the object itself. So if there are no external forces, then the body will have 0 torque, and therefore the momentum will not change. So we have the same law as we have in Newton's linear physics, which is absent any external forces, the total momentum does not change. Absent any external torques, the total angular momentum does not change. Okay, so here I was proper and capitalizing and italicizing the torque because it's a vector. And this slide wants to emphasize the point that whereas you can calculate F and P without regard to the coordinate system, here you have to calculate torque and angular momentum with respect to the position relative to the axis of rotation. We're talking about rotation about an axis, and so exactly which axis you pick makes a big difference. And it changes the value of the torques, and it changes the value of the angular momentum if you pick a different rotational axis. So we have these depend on the position, and these only depend on how position changes. So there's a dichotomy here between linear and angular. But the equations look very much the same. So we worked hard to keep the equations from changing. And the main motivation for that is once we learn to solve one set of equations, Now, if the equations don't change, all of our techniques work on those new equations as well. There is in three-dimensional rotation something important called the principal axis theorem. And that is that any body that you can imagine has three rotational axes that are all mutually perpendicular to one another. They're mutually orthogonal. And the three axes all run through the object's center of mass. So they are the yellow axis, the red axis, and the black axis, which is pointing in and out of the screen. And if you spin the object around the axis, any one of the principal axes, it won't wobble. It'll just turn. If you try to spin the object around an axis like this, diagonal, it's going to wobble like crazy because it it doesn't have the same moment of inertia as we'll describe shortly as it rotates. So, but if you stick to the three principal axes, then the rotation will be as simple as possible. The object will just turn, and there won't be any stress on the axle, and there won't be any confusing forces that will arise. So no matter how crazy this object looks, there will always be three axes that are perpendicular to each other that you can rotate the object about without encountering any excess forces. So we always look for those principal axes, and then we define rotations in terms of how much of this principal axis rotation, how much of that one, how much of the other one. Okay, so we're going to call the three principal axes X, Y, Z because we're enormously creative. So we always use the same thing. And with respect to those axes, there's an angular velocity. It could be rotating about any of these axes by different amounts. As it rotates, there's a certain angular momentum, which is this looks like the same thing as a linear case. In the linear case, it's mass times velocity. And here it's moment of inertia times angular velocity. So moment of inertia is the equivalent of mass in rotation, and angular velocity is the equivalent of velocity in linear physics. But it's the same format as the linear equation. The linear equation would be that P, the linear momentum, is mass times the linear velocity in X, mass times the linear velocity in Y, mass times the linear velocity in Z. And the rotational kinetic energy is, we said, 1/2 I omega squared, but you can also write it this way. This is equivalent. This is the angular momentum times the angular velocity, 1/2 of that. Okay, so if you have a body composed of a large number of particles n, then and it's the entire body is rotating at a constant angular, at an angular rate omega, which may or may not be constant, then the velocity of each particle, as we showed above, is given by this equation, and the angular momentum of that single object is given by this equation. And we can rewrite VR according to this equation. So we get R squared omega. And now we get this equation here, that the total of all of these summing over all of the different particles is this thing here. The masses, the omega is a constant for all of them, right? And it may change with time, but for at any given instant, all of the particles are moving with omega. And so now we can write, we can take all of this stuff here, and we can call that I. And we have an equation which looks like the linear equation. It was P, the linear momentum, is mass times velocity. Here, the angular momentum is is the moment of inertia times the angular velocity. And I is just all of this stuff here. Okay, so we have managed to define these quantities, this torque, the angular momentum, the moment of inertia, so that we get back to the equations that we know how to solve. And again, I is the moment of inertia of the body. And this is the equation for how to calculate it. And if all of the particles have the same mass, then you can take the m out here, and you're just taking the average of all the distances squared. So if a particle is further from the point of rotation, then it's going to contribute more to the moment of inertia than if it's very close. And that makes sense. It's a lot harder to spin around an object that's far away from the axis than it is to spin around an object that's close to the axis of rotation. And I'm not, don't worry about the slide. There's no test. If you needed to calculate the angular momentum of a body, it's in this table for all the most simple shapes. And you have to define the axis of rotation of the moment of inertia is different in different axes. Obviously, if you rotate this thing about this axis, it's going to be a lot easier than rotating about the axis in which a lot more stuff moves a lot further. Okay, so that gets us to something fun. And that is, if you've ever seen Olympics skating or some national or international competition, ice skating, then you've often seen the performance come to a conclusion in which the skater does this motion, which is called a scratch spin by the people in the trade. And the motion is that the individual will start turning, rotating around. You see this foot is off the ground. This foot he's spinning on the tip of that skate. And he's spinning around with his arms and leg outstretched. And then he pulls his arms and legs in. And all of a sudden he starts spinning really fast. And it's very dramatic, and it's a lot of fun to watch. And it's probably very difficult to do, but they all do it. So why does this work? There's no force being exerted on this individual. Why is he able to spin faster all by himself with no external force? Where does the energy come from, in other words? Okay, so the angular momentum is the moment of inertia times the angular velocity. That's what we have at the start. S, the subscript S will be start, the subscript S is finish. So this is start, this is finish. Okay, so when he pulls his arms and leg in, the leg, which is the axis of rotation, has to stay relatively fixed, but he can pull the other leg in. He's crossed the leg. He is reducing the radius of all of his arms and legs about the axis of rotation. So here's the axis of rotation. He's got his arms stretched out as far as he can. He's got his legs stretched out as far as he can without falling over. And then he pulls them all in. So he's reducing the R, right? And this is R squared. So if you cut R in half, you've cut R squared by a factor of 4. So since the R squared at the end, the finish is much less than the R squared at the start, then the angular momentum, this is the equation here, I'm sorry, the moment of inertia at the end will be much less than the moment of inertia at the start. And go back here. If you dramatically reduce this, you have to dramatically increase that in order to keep the total amount of angular momentum constant. The total angular momentum is constant because there's no external forces. And so what do they actually achieve? By reducing the radius, they make the moment of inertia much less. Therefore, since the product has to be constant, therefore the final angular velocity has to be much more than the beginning angular velocity. And skaters can typically do this. They can go from 2.5 full rotations per second, RPS, rotations per second, to 6 rotations per second. So that's between 2 and that's 2.4 times, nearly 2.5 times faster. He's turning around because he has managed to pull his arms and legs in. So he has reduced, they are able to reduce their R by a factor of 1.55, and you square that and you get that R, the I, the moment of inertia, is reduced by a factor of 2.4. And so I'm sure all of these people studied diligently their angular momentum before they learned to do this, but whether they did or not, they do it very well indeed. Any questions about how that works? Okay. This addresses the bizarre, the idea that you could rotate the object about something other than its principal axis. So if you rotate this blob, not about its own axis of symmetry, but about the z-axis, then you're going to have a very different moment of inertia. Moment of inertia, like torque, like angular momentum, depends on the axis of rotation in addition to the properties of the body itself. And this is the parallel axis theorem. This is the moment of inertia it would have if you rotated the body about itself. And sorry, this is the moment of inertia of the body rotating about its own center of mass. And this is the amount you have to add if the center of mass is displaced a distance r from the axis of rotation. So if you're rotating a cylinder about its axis of symmetry, you have a relatively low value of moment of inertia. If you rotate it about its end, then a lot more stuff is moving a lot faster to go around. And so the moment of inertia is increased by this quantity here. And this is a derivation of that equation, which I'm sure you will all be diligently reading at 11 o'clock at night. That's the proof. I leave it there, not because you have to learn it, but because some of you want to see the math, and there it is. Okay, so the last thing.
So quick question.
Yeah.
Back up two slides if it would.
One more.
Right. So if you have a whatever entity, let's pick a ball, since it's the simplest thing.
Yeah.
The further away from the first term says the further away the ball is from z, vertical axis z,
Yes.
the higher its moment of inertia.
Right. The more difficult it is to rotate. Well, let's imagine this is a ball and it's tied to a string and you're whirling it around your head.
Yeah, yeah.
The longer the string, the more force you're going to have to exert. Because you're accelerating that mass to a greater degree. the object.
Oh, okay. So, okay, that's kind of, okay, thank you. The reason I say thank you is because if you look at an old steam engine, or and you see one of the things they did is they introduced this little thing at the top, where as the pressure builds in, when it starts to build to a certain point, this valve effectively starts rotating. And when it rotates enough, it releases pressure. So I was trying to figure out how that works. And I guess when the pressure increases, it increases. It gets the balls on the valve rotating fast enough that it eventually, when the pressure gets high enough, it releases steam.
Oh,
But okay, thanks. Now I know how that valve works. Okay, thank you.
I never heard of that sort of thing, valve before, so now I have to go check it out.
Okay.
Okay, and this is the total kinetic energy. This shows you the derivation that the total kinetic energy can be written in terms of the moment of inertia and the angular velocity. And that's equivalent to just taking the sum of the linear kinetic energy. So you can either calculate the kinetic energy of each individual particle as it moves around in the old Newtonian way, or you can take this equation here. If you know the moment of inertia and the rotational velocity, then you don't have to worry about what all the particles are doing. That's what I worries about. Okay, now we want to talk about gyroscopes. And gyroscopes are somewhat magical because they do things that no one would have guessed in advance. I presume no one would have guessed. They simply they seemingly defy the laws of physics, but if you really understand angular momentum, then their motion makes sense. So if you spin a gyroscope very fast, as indicated here, then it doesn't fall down. If the gyroscope wasn't spinning, if it was a simply inert, simple object, gravity would immediately topple this thing over and would fall on the table. But if you spin it fast enough, the gyroscope won't fall at all. So it seemingly defies gravity. And I've got a couple of YouTube videos to back all this up. And so there's a downward force of gravity, which we could say is exerted on this point, or on the center of mass is more proper. And when that happens, the gyroscope turns. It doesn't go down, which is the direction of the force. It moves in a direction which is perpendicular to the force because of the definition of torque. And here's the definition of torque. It's the radius vector r time cross product with the force. And so it's a horizontal force, and it rotates the tip around this dotted ellipse. This is a circle viewed on edge, so it looks like an ellipse, but it's a circle. And so the angular momentum changes as the thing goes around, because the angular momentum is defined as with respect to the axis of rotation. So the angular momentum changes because the torque is not zero, and the gyroscope moves around. So let's see. And if you have a gyroscope and you is moving around very rapidly, and you're holding the tip, and then you let the tip go, it won't fall down. What it'll do is this motion here, which is called a cycloid. It'll dip a little bit, but it'll spin around, and this is called a nutation. So let's let me see if I can bring up these other videos. Never tried this before. Okay, do you guys see the gyroscope here?
We see the view graph with the gyroscope on it, yes.
Yeah, you see the gyroscope, okay? Then I will play the video.
This is a gyroscope. It consists of a metal wheel mounted on an axle. The wheel and axle spin freely, secured in a metal frame. This simple device can behave in the most unexpected ways. The components of this simple mechanism are obvious, and it doesn't seem to have any special capabilities. Try to stand it on end and it falls over. Try to suspend it like this and it drops. Apparently it can't defy gravity. But spin the wheel and all that changes. A string provides a simple method to spin the wheel.
What happens when the prostate enlarges and the urine channel gets tight? If you have an enlarged prostate, do this 5 seconds, Japanese.
Sorry.
The first thing I notice about the spinning gyroscope is that it resists attempts to change its position. A resistive force appears when I attempt to tilt or rotate the gyro. Now when I stand it on the tabletop, it stays vertical. The spinning wheel
Bob,
is creating
all we're
force
seeing
that
is
holds the gyroscope
one view
upright.
graph.
I'm
When the wheel
sorry.
stops, the force
There's
doesn't
no movement.
All we're seeing is one view graph. Says
You're
gyroscopic.
not seeing the video?
tension. No, sir.
Oh, shoot. Hang on.
But the video sounds great.
Okay. I lost control of Zoom. Oh, well. Best laid plans, huh? Oh, there it is. Okay. The control bar just changed. Do you see the gyroscope now? It's not turning, but do you see it?
Yes,
Yes.
Okay, here we go.
there we go.
A spinning gyroscope will balance on a string. You can even lift the gyroscope with a string looped around one end. This interesting behavior is difficult to explain. Physicists have determined that a rotating wheel has angular momentum, similar to the momentum that a stone flying through the air has. To change the direction of the stone requires a force. Similarly, changing the orientation of the rotating wheel requires force. The spinning wheel prefers to stay oriented as it is, and it resists any attempt to change that orientation. The fact that gyroscopes will maintain a particular orientation in space is very useful. In modern aircraft, an inertial guidance system uses spinning gyroscopes to monitor and control the orientation of the aircraft. The gyroscope is suspended in a special cage that allows it to maintain its orientation independent of the aircraft's position. If the aircraft rolls, electric sensors and contacts connected to the gyro send information to the pilot about the aircraft's orientation. The Mars rover explores the surface of Mars using spinning gyroscopes to provide stability and navigational information. This full-sized robotic helicopter flies without an onboard pilot. Gyroscopes provide stability and navigation. Gyroscopes have become essential components of aircraft, ships, robots, and spacecraft. If you're interested in experimenting with a gyroscope, they are available from online science and hobby retailers. The gyroscopes I'm using are manufactured by Tedco Manufacturing in Hagerstown, Indiana.
Okay, we can avoid the commercial. And I've got another one. Okay, can you all see this guy sitting in the chair?
Yes.
Okay,
So in this demo, I'm on a nice little chair that rotates, pretty low friction. I also have a nice bicycle tire that's got some handles on it.
this is from
What I'm
Austin,
gonna do is
Texas.
I'm gonna have an assisted divine spin this thing. And as this thing spins, it's going to have some angular momentum. And the question is, if I turn this thing, if it's spinning in one direction and I flip it to one side, I'm changing the angular momentum. Because of conservation of momentum, I have to compensate for that by adding my angular momentum. I might start spinning to cause myself to maintain this total angular momentum or conserved angular momentum. So I'm gonna lift my feet off the ground, try not spinning. The system's gonna come and spin this for me. Some angular momentum. Now when I rotate it, start to spin. If I want to stop myself, stop. If I go the other way, I spin back around.
Okay,
And essentially, me and this bicycle wheel are one isolated system. The platform sort of isolates it. And as long as there's no outside
Right,
or taking
right, carefully.
to that acting, then me and this bicycle wheel.
are we still
are
listening to the
fundamentally
guy?
Okay.
Okay,
All right, so if it does have a lot of angular momentum already, and I try to change it by flipping it over,
okay, I'm
what
sorry.
things can happen?
We have,
I guess that's what no, are you recording? I guess I should. Yeah. All right.
okay, anyway, that was my experiment to see if I could get away with showing someone else's video. I want to wrap up by reviewing the highlights of this course. These are all things we've discussed before, but I'm collecting them at the end here so that if you want to go back later and just review the highlights of the course, there's one place you can look. And so we began by talking about what is science and what is physics. And science is our best effort to understand nature. And we do that by developing, by gathering as much data as possible, making observations and experiments, and trying to develop models, ideas of how nature works that we use to explain the data. We test those models by looking at the experimental observations, and we reject models that don't match, and we work further on models that look like they're promising, and we will gradually make progress. And as they say, pursue the least inadequate description of truths. So physics is that field of science which explores the most fundamental and most extreme of natural phenomena, the biggest, the smallest, the lowest energy, the highest energy, and so forth. And all of the other sciences, we physicists would claim, use physics as their foundation, as well as all branches of engineering. And physics describes the relationships among the various entities of nature, entities being primarily energy, space, time, matter, and charge. And these are concepts that we can't completely define. We can't tell you exactly what charge is, but we can tell you how charges interact with one another. And that's the limit of what physics can achieve. And these are the primary elements: space and time, energy in many different forms, principally in classical physics, kinetic energy and potential energy, and matter in various states, including the state of matter of being solid, liquid, gaseous, or finally at the highest temperatures, plasma. We talked about these conservation laws today. We believe that total energy, total linear momentum, and total angular momentum are conserved because of fundamental properties of our universe, mostly that it doesn't have any holes. And there are three other conservation laws that we don't have a fundamental basis for predicting, but are confirmed by extremely precise measurements. And that is the total electric charge, the total number of quarks, and the total number of leptons. We talked about Newton's laws. The first law being that absent external forces, the velocities of all objects remain unchanged. Second law, F equals ma. If you apply a force F to a mass m, you cause that mass to have an acceleration a. And the third law, for every action, there is an equal but opposite reaction, which we used today. Newton developed the law of universal gravitation, and that is that any objects that have mass exert forces upon one another according to the equations shown here. F is the force that each body exerts on the other. So that's the third law. The force is the same. The reaction to the force differs because the masses differ, but the forces are the same. G is a constant called Newton's gravitational constant. M is the mass of one body. Uppercase M is the mass of body number one, lowercase m, the mass of body number two. And R is the distance between the centers of one and the centers of two. And if the bodies are extended, then this equation applies if they are of uniform density, regardless of the size of the objects. We talked about the development of classical astronomy. The principal laws there are due to Johannes Kepler. He proved that all planets orbit the sun in ellipses, and that proof extends to other objects or orbiting other massive bodies like a star orbiting a galaxy. The massive body that's creating the main gravitational field will always be at one of the focal points of the ellipse of the planet's orbit. Each planet has its own ellipse, but the sun is at the focal point of each of those ellipses. Each planet sweeps out in its ellipse an equal amount of area in equal times, is the second law. And the third law relates the period of the orbit to its semi-major axis. If it's a circle, then the semi-major axis is the same thing as the radius. So here, m is the mass of the central body in the solar system, that's the sun. T is the orbital period, for instance, 1 year for Earth. R is the semi-major axis, which for a circle, as I said, is the radius. And m to the first power times t to the second power is proportional to r to the third power. And indeed, we still use that equation 4 centuries later to calculate the mass of galaxies, for example. We see a star moving with a velocity that will result in it having a certain period. For the sun, that would be about 200 million years. And we look at the distance from the star to the center of the galaxy. And then by using this relationship, we can calculate the mass of the galaxy. And we find primarily that most of the mass is not in visible stars. So that's one of the proofs of the existence of dark matter, is using Kepler's law. We talked about several things that are illustrated here. This graph shows the force between two atoms as it varies with the distance between their centers, r being the distance between their centers. And the two atoms will have a stable equilibrium at some value that's called R0. So they don't want to be too close and they don't want to be too far. If they were set at R0, they would stay exactly where they are. And this is a local minimum of the potential. And at any local minimum or maximum, the slope of the line tangential to the curve is always has zero slope. It's always a purely horizontal line. Otherwise, it wouldn't be the minimum. And so we're doing a Taylor series expansion here, and the B1 term is absent because the slope, that's the slope term, and the slope has to be zero. So we end up with the leading term being the x squared term, x being the deviation from the equilibrium. And we can ignore the higher order terms if x is a small enough number. So if x is small, then x cubed and x to the fourth and x to the fifth will be all much smaller than x squared. So the rate of change of u is given by this, plus a bunch of terms that we can ignore because they will be much smaller. And that's the basis of Hooke's law. This is the law developed by Hooke at the same era of Isaac Newton. And the constant of proportionality is called the string constant. So it depends on the properties of the string. But the motion that comes from this equation is independent of, for instance, the mass. Well, I mean, it depends on the mass in this way. So if you bounce, if you have a weight on the spring in equilibrium and you pull it down and let it go, then it's going to oscillate back and forth. And all of these motions will be in terms of sinusoidal motions because of this relationship. This sort of equation has solutions which are either sines or cosine functions. The same idea applies to pendulums. There is a point of equilibrium, and if you move the pendulum from the point of equilibrium, it will oscillate back and forth with a sinusoidal function. And this would be the frequency, and the amount of displacement depends on how you start the pendulum. We talked about thermodynamics, and which is the physical theory that deals with heat, work, and gases, and was made a major contribution to the development of steam engines and those sort of heat engines that drove the Industrial Revolution, replacing human labor with machines that were driven by the conversion of heat into work, according to the restrictions of thermodynamics. And that allows us to define in a proper scientific way things like the pressure and the temperature of a gas. That the pressure is proportional to the average kinetic energy of the particles of the gas. The second law of thermodynamics, which is notorious in the public literature as well as in science, states in various forms that in any macroscopic process, the total amount of disorder will always have to increase. So a crystal is a perfectly ordered material. If you step on it and destroy the crystal, then you have an object of much higher disorder. And the second law says that the net result of any process has to be to increase the amount of disorder in the universe. We talked about the operation of steam engines and internal combustion engines, and they're all based on this Carnot heat engine concept developed by Sadi Carnot in the 18th century, I think it was. And he developed equations for how much work you could get by removing heat from one hot body and dumping the waste heat in a cold body. And the process is most efficient if the hot body is much, much hotter than the cold body. If they were the same temperature, you could get zero work out by transferring. You wouldn't be able to transfer heat from one to the other because they would both be at the same temperature. And this is the steam engine that was whose design was improved by the development of the equations of thermodynamics. And today we talked about rotation. And so I showed this comparison of the similarity of the equations of linear motion and of rotary motion. If we define these new concepts in a proper way. So the new concepts are moment of inertia, replacing mass, torque, replacing force, which should be a vector, and angular momentum, replacing linear momentum. And that explained why you can see this beautiful performance in an ice skating presentation when the skater pulls in his arms and legs, or her arms and legs, reduces the average radius of the body, and that increases the spin rate dramatically. And lastly, we talked about gyroscopes and the strange properties that they have, which seemingly defy intuition, but are consistent with the rules of angular momentum and torque. And I'm presenting next a collection of all of the new math that we learned in order to understand these physical effects. And I'm not going to go through the math, but I've collected it all here so that if you want to refer to any of this, it's in the recording, and you can, you don't have to look through 5 lectures or 6 lectures to find it. All of the important pieces of math are here at the end. Okay, that's the end of the math. Okay, so we have time for any question that pertains to the course that we have spent 6 weeks working on together.
Robert, as you know, I really love math, and this was a great, great course. But what's your next course?
Well, I propose, and I would very much like to hear everyone's feedback. I propose to do Physics 201, which is about electricity and magnetism.
Oh, interesting.
So we've talked about mechanics this in Physics 101. And in Physics 201, we're going to talk about what is electricity, what is the electric field, what is this business of magnetic fields and electric fields, what is an electric motor, what is an electric generator, how these things operate, and the various properties of radiation, which will include a discussion of how radio and TV signals are broadcast through the air. Why do you get to listen to your favorite music while I get to listen to my favorite music? Even though the world, the air is filled with all these different signals. And I think that would be a very interesting. And it doesn't have as much new math as this did.
Oh, bummer.
Oh, bummer, yes, right.
I think that's a great idea, and thank you for gathering all those equations together so they could be readily found.
Thank you. You're welcome.
Robert, your classes are absolutely fascinating. So I just hope you keep teaching.
Well, I think 201 may be my last.
Uh-oh.
I'm running out of new ideas. So if you really want me to keep teaching, you have to supply me with ideas as to what you want to talk about, because
About the James Webb Space Telescope, what's going on there? And
yeah, that's one topic.
yeah, you know so much about what's going on out in the universe that they're
That
influenced.
would be very interesting.
Yeah.
Also,
Okay, well, maybe I'll add that to Physics 201, because it doesn't merit a standalone course. It's a one session conversation. I think it's doing great things, and I think 5 years from now we'll really be able to say something dramatic. But at this point, the data is exciting, and it's not yet clear what it all means. I mean, for instance, they are talking about what they have a different interpretation of what the data is this month than they did 3 months ago.
Wow.
And maybe that's interesting to see how these things evolve, but it's a sort of a strange class, because you teach one thing and 3 months later it's replaced by a new vision.
That
Oh, life.
is interesting. The fact that what they know is changing.
The 10-second version of an explanation is, we see these really bright things at very early times, and they thought they were galaxies, and they were at such a loss to figure out how the galaxies could exist at such early times that they thought the whole theory of cosmology had to change. And now they think that these very bright things aren't galaxies, they're stars. They're immensely large stars. They're millions of times the mass of the sun, they think today. And so the conversation about how the first galaxies formed is no longer the conversation. It's, how did they get these stars? And that's very exciting stuff, but it sort of doesn't fit into a class setting nearly as well, because the answer keeps changing. I don't like explaining something and it turns out the explanation is no good 3 months later.
Well, understanding why it changes would be interesting too.
Yeah. I mean, I don't have a problem talking to scientists about how bizarre that these things are, because scientists know that things change. But you give a lecture to a class and you're supposed to know the answer, or why are they paying to hear you?
Robert, we know you're a genius, so don't worry about it.
Well,
We love their classes.
Well, that helps you identify with the CDC as they proceeded to explain COVID over those many months, and the public was frustrated.
I'm so glad that wasn't my job. Have you guys seen that film about Fauci?
No,
Oh, it's on Netflix or something. It's a great film. It's about 2 years old. I mean, you know, they made it about 2 years ago. It's a really interesting film about Fauci. It's, I think, 2 hours long. I mean, it's pro Fauci, but it's very interesting, his career. He sort of led the charge to find a cure for AIDS, and that was very unpopular. And he's an old man. I mean, he's older than I am even. And he was leading the charge on COVID. Really, really incredible guy.
I had a, Robert,
Not that he didn't make mistakes, right? They talk about that, but you know, if you're looking for God, you don't find him, you know, with 2 legs and 2 arms walking the surface of the earth. All right, he doesn't work for the God does not work for the CDC. Humans work for the CDC, and they make mistakes. I'm sorry.
Robert.
Yeah, Gil.
Robert? Yeah, I had a chance to hear him speak probably about 5 years ago, and he relayed essentially the whole history of his coming to the National Institutes of Health, and and actually became an authority on autoimmunity back then when he started treating a condition that I had in my field of rheumatology of ischemic of vasculitis with steroids, and he showed all of these different presidents that he'd met during that time frame, and essentially relayed what he has subsequently relayed is that, yes, you have the evidence, and then just as you said with regard to what they're doing today, things change. And
Yeah.
you have to adapt.
Yeah.
And he's, you know, absolutely brilliant, and you know, what have been portrayed as mistakes made. You know, 50% of what he said was true, and then 50% wasn't, and that's pretty good for a scientist.
Yeah. Well, I mean, that's the batting average Einstein had. And every other physicist is a hell of a lot worse than that.
Right.
So, yeah.
You know what I
I mean,
wanted to,
50% batting average is not good for an airline pilot. But if you had a 50% batting average in baseball, I mean, you'd be the league MVP. I mean, no one has ever had a 50% 500 batting average in baseball, right?
no.
I mean, it's just I mean, if you tackle the unknown, you're going to be wrong at least as often as you're right. But thank God we have people like that.
Robert, I was interested to see, this is sort of off a little bit in terms of topic, but I was interested in, before your talk, I was listening and have this week to the Murdoch case of South Carolina, the murders.
Yes,
You familiar with that?
Yeah, yeah.
Well, what's most interesting today in the last day or two is they have been discussing the physics and electrodynamics of the gunshot wounds.
Really?
And they brought on the stand a pathologist and also somebody who was acting as a pseudo engineer to try and determine exactly what you were discussing in the first part of your presentation today as to which way the bullets and their fragments would go, and trying to get these people to say whether there was one or two, you know, guns involved.
Hmm.
And then the next thing they did was to have a guy talk about the velocity of phones, and what happens when you take a phone, an iPhone, and toss it out the window of a car, and whether the iPhone in effect goes on or not. And he was explaining on the stand, and I was thinking about all these jurors who had to sit here and listen to this and determine essentially the physics, and they did this for hours.
Hmm.
I couldn't believe that this was actually being done, but it was really about mechanics and physics and all the electronics of what was going on. And it's in present day, you know?
Yeah, interesting that that much science is presented to a lay jury,
Right.
and they're not allowed to ask for help,
Oh,
right? They have to listen, and that's it. I mean, for instance, if I was on that jury, I
Yeah.
would be disqualified because I was an expert in the field of the evidence being presented.
Not necessarily.
No?
no.
No, not necessarily. There are some courts that will allow jurors to submit questions. Whether the judge will allow that particular question to be asked is up to the judge.
I see. Okay.
Uh, the concept of juror eligibility, can I talk just for a couple of minutes? You probably would get stricken because these lawyers have a certain number of peremptory and challenges if they can't think of a reason why you ought to get struck for cause. And one of my theories is, I knew some trial lawyers when I practiced. I was not a trial lawyer. But the thing that I gathered that the trial lawyers wanted to do was to strike from the jury all of the people who were well educated, as Piccioni may be, and all of our friends here. And they also wanted to strike people who were strong-minded and who might push the jury around to a conclusion. I mean, there's a whole psychodynamics of this. I was on several jury panels, never got picked.
Mhm.
But anyway, I find the case fascinating too. And it is an example of the press of public opinion, an awful murder or two, and the population wants somebody to go to trial and somebody to be punished. And in a case like this, there's only one guy out there. And a friend of mine had an alternative theory that he was sharing with me at lunch a few days ago. A little bizarre, but you can get your mouth around it. His theory was that this Murdoch had stolen from his clients, no doubt about it. And his theory was that some of the clients had killed the family to get even,
Hmm.
on the theory that if they'd killed Murdoch, they would have been, target right away. But if you take after the family, he's the target and not the client. I think it's a bit far-fetched, but if you want to write your next novel, there's a plot line.
Or the closing argument of the defense.
Well, that is going to be something like that will be the closing argument of the defense. And if they can't figure out how many guns there were, that may be the reasonable doubt to the case. Anyway, I enjoyed the talk as well, Robert, and I think you should work hard to find out what Physics 301 is going to be. One of the things that I'm interested in knowing about, I'm not sure it's easily within reach, is the question of the physics and chemistry of a silicon chip that's part of a computer. that may just be something you put up for one lecture and just talk about how that gets done, how it got done in the beginning, and why it has been able to be improved so immensely over the last, I guess it's been the mid-50s since the founder of Intel was a rookie assistant professor at UCLA working on how it is he could get more than 4 transistors on a chip.
Well, I do have a discussion about semiconductors, but it's more about how they work than the history. So maybe I'll.
Well, no, I would be happy to, I would be delighted just to know how they worked. I mean, I just know a little bit that I'm not remembering the inventor, the founder's name.
Gordon Moore?
Moore. Yeah, Moore was a graduate student at Caltech, you know this.
Yeah, I
Yeah.
met him one day.
The post PhD went to work at UCLA, and then he drifted off into industry.
Right.
Fascinating story. But anyway, I did enjoy the talk and this lecture series, and we'll all work on figuring out what Physics 301 is going to be.
Okay.
Let me propose something for Physics 301 that you could entertain it or might be too disjointed. Oftentimes in Scientific American, even though they've attempted to make it less rigorous than it once was, you get to the end of the article on physics or astrophysics and you say, and you haven't quite completely wrapped your mind around. So if we gave you suggestions like, look at this article and explain it to the mortal man, maybe you would consider that.
Yeah. Yeah. Well, there are a certain percentage of those articles that I have some expertise in that area. Certainly many that I don't. Okay, well, it's been a pleasure for me, and I will
Thank you.
send out a newsletter announcing Physics 201 in the next week or so. I've got a lot of backlog on the to-do list at home.
Okay.
So I'll take a week off at least.
Okay, thank you.
Okay, anyway, if you guys have questions, you can send me an email. I mean, if you think of this course and you say, oh, I forgot to ask about that, just send me an email and I'll respond.
Okay.
Okay, so thank you very much, and
Thank you.
see you next time.